So the first one that we will be talking about is the hypothesis testing for proportion. Now, what is hypothesis testing, or how many hypotheses can we have? So hypothesis testing is just a statement, but it contains two statements. The first one is the one that we call the null hypothesis, and the second one is the alternative hypothesis. The null hypothesis is a no change hypothesis. Usually, we assume this one to be the no change always. So numerically, this one for the null hypothesis, we use the equal sign. We use the equal sign usually, okay? And the alternative hypothesis, we use the other inequalities other than this equality. So alternative hypothesis is this is not true. It could be less than, it could be greater than, or it could be not equals. So we have the not equal option, we have the greater option, we have the less than option. Okay, so all this one they make the alternative hypothesis, either one of them. Just choose one of them depending on your problem, and that will be your alternative hypothesis. Now, if we choose the first one, then we will have a two-sided alternative hypothesis, and these two, they will make up a one-sided alternative hypothesis. Okay, so when we have this greater or less than, we call the alternative hypothesis one-sided, and if we have the not equals to, we call it a two-sided alternative hypothesis, and this will choosing which one of this makes difference in our final decision, and we will see what the difference is between those three. All right, now for proportion, if our test is about proportion, then the way we write the hypothesis is the first one, H naught or H sub naught, or the null hypothesis, is given by P equals to P naught. This P naught is just a number. It's some number, some given number, some given proportion. But this P is the variable, the parameter. So for example, I can write P equals to 0. Let's say 7. Okay, so this is what I'm using the P naught to denote to. And then, as we said earlier, H sub A can be P naught equals to P naught, or H sub A P greater than P naught, or P less than P naught, depending on your problem. Always you have to be careful on choosing this alternative hypothesis. It's the most important one, to be honest. And sometimes instead of just alternative hypothesis, they call this one, or this one is called the researcher's hypothesis. Okay, for example, the prosecution, for example, in trial, if we consider the prosecution team as a researcher, they try to find evidence to convict the defendant, for example. So the defendant is innocent at the beginning, like that's the assumption, and then they try to find evidence to convict him, right? So that's what we are trying to do. So always it's important to choose the alternative hypothesis properly. That's the most important thing. And then we have the critical value. And this critical value is the same with the critical value that we have been using in constructing confidence interval. So to find the critical value, it depends basically on the confidence level. For example, if I consider the normal distribution or the Z table distribution, then if, let's say, I give you a confidence level equals to 95%, then the middle part is 0.95, and the leftover, this both sides, the sum of these two sides was 0.05. So 1 minus 0.95 is what we call alpha. Okay, that's what we call the alpha, or the significance level, which means this one. And the critical value is this point, these 2 points. Those are what we call the critical values. Okay, and that's why we set the cut point. So the significance level, if we come to this point, let me bring it here. The significance level is just alpha equals to 1 minus 95. Let me use this instead of 0.5. I would use just to make it general, 1 minus C, where C is the confidence level. So as an example, I can write alpha equals to 1 minus 0.95. Okay, so just this is an example, but in general, alpha is just 1 minus C, which means basically alpha is the leftover. If I give you a confidence level, then what is the leftover? Let's say if this is 99, then it will be 1 minus 0.99. That's what we call the alpha level. And we will see why we are trying to find this alpha level, because we're going to use this one to decide which one to accept, whether to accept the null hypothesis or the alternative hypothesis, whether the defendant is guilty or not guilty. And then we have this p-value. I will come to this because it's much more easier to look at this one after we see the example. So let's jump to the next step, and then we will come back to this one. Now, the steps to perform a hypothesis test. Okay, hypothesis test. The first step is to state the hypothesis. What is your alternative hypothesis, and what is, of course, the null hypothesis is usually obvious, so that one is not too hard to figure out. So H sub naught is, in this case, for example, if our problem is about proportion, then H sub naught will be P equals to some value P sub naught. And the alternative hypothesis will be one of the three. So let's say, for example, it is the no equals to not equals to P sub naught. So this is our alternative hypothesis. As I said, you have to be careful when you choose the alternative hypothesis. The null hypothesis is fine because it's more or less it's the same. When you go higher in higher level courses, maybe you may see different null hypotheses, but in this case, we are only considering this one. And another point that I wanted to mention here, if there is no indication that the alternative hypothesis is a greater or less than, then always use this not equals to. Okay, if there is an indication to check whether it's greater or less than, then depending on the problem, pick one of this. But if there is no indication about that, always pick the not equals to hypothesis, alternative hypothesis. All right, and the next is, what is your model? Because we need the model in order to perform the hypothesis. So when we come to proportion, when we test a hypothesis about proportion, then we use, if you remember, for confidence interval, if it is about proportion, we would use the Z table or the Z model. And here, similarly, we use the Z or the normal model. Therefore, the conditions for performing a hypothesis about proportion are, we have the independence, we have the 10%. If you remember, they have to be independent, they have to be random. We need to have less than 10% of the total population in our sample. And then we have the success failure condition. So we have to check if all these are satisfied. Otherwise, well, we cannot test the hypothesis if these are not satisfied well, or if we are not confident about these conditions. Therefore, always you have to check the condition before you go and do the work. So here I mentioned, if the conditions are not met, either you have to quit or redesign your study. So this is for practical real research, but here, when we have some problems, we have to check for the conditions.
I'm sorry, you said it was more than 10% or less than 10%?
Less than 10%.
Less than 10%.
Less than 10%,
sorry.
yes.
Thank you.
Yeah, so your sample size, this is about, we are talking about the sample. So the sample has to be less than 10%. All right, so suppose if these conditions are, or if we assume these conditions are satisfied, then the model, the formula for the Z is given by, why is not writing? Z equals to P minus, this is P hat minus P sub naught over the standard standard deviation of P hat. Now, you may ask, like, why do we use standard deviation of P hat? Why not standard error of P hat? If you remember, for a confidence interval, we would use Z equals to P hat minus P over standard error. Or let me write it in a different way. Let me write. So when we write the confidence interval, we would put P hat plus or minus Z asterisk, the critical value, times the standard error of P hat. Okay, so this is the confidence interval. So why do we use here standard error but not here? Here I'm using standard deviation, but here we're using the standard error. And the standard error is, this is confidence interval. The standard error of P hat is given by the square root of P hat Q hat over N. And here the standard deviation is given by P sub naught Q sub naught over N. Okay, so the reason is because here I have this value, the claimed value. Here we have this claimed value. So because we have this null hypothesis, And the first assumption that we have before we prove it is not true is that P equals to P sub naught. Therefore, I will use this number as my population proportion, okay, as if it is true. And using that one, considering that one to be the population proportion, I will use it to find the standard deviation. And if you remember, if we know the population parameter, then we can find the standard deviation. But if I don't know the population parameter, which is the population proportion, then I use the sample proportion, which is p hat, and we call this the standard error. And that's why here we don't have any population value. So we use the sample value to estimate it. Therefore, we call it the standard error. But here, since I have it, I find the standard deviation here. Okay. Therefore, the model is given by z equals to p hat minus p sub naught over standard deviation of p hat, where the standard deviation is given by this value. We know this z is normally distributed. Okay. Okay. So the z is normally distributed, and okay, the model here is normal model. All right, and then next is the mechanics, and this is basically the calculation. So here we do the calculation. Since here we don't have the numbers, I cannot find the calculation. And then the final is, well, here what we do is you calculate the of course the standard deviation of p hat, and then the z value, and then the p value. Well, still we don't know what p value means, but we will see what that means. So, and then finally we go to the conclusion. What we do is, if p value is greater than alpha, then we fail to reject H sub naught. Okay, if p value is less than alpha, then reject H sub naught. So this is the importance of the p value. Okay, if p value is less than alpha, if it is very small, that means be careful here. It's not when it's big that we reject H naught. If it is very small, then we reject the null hypothesis. If it is bigger than alpha, then we fail to reject. Now here I didn't say accept H naught. I said fail to reject H naught. We don't know, we cannot say we accept H naught. We don't accept H naught, but we fail to reject it because we don't have enough evidence. Remember, when when they don't find enough evidence, the defendant doesn't mean the person is innocent, right? It's just they couldn't find enough evidence. And that's what we are saying, because all this decision that we are making is based on our sample. And based on what we have, our sample is our evidence now. So based on what we have, we cannot agree with the null hypothesis. So we fail to reject it. But if I have enough evidence, if this is true means I have enough evidence. So I reject the null hypothesis and I agree with the alternative hypothesis. Okay. Now let's consider the following example, and I will go back to the definition of p-value. So I have this 80%, but a newspaper reported a survey of 90 randomly selected. So this is important. 90 randomly selected local teens who had taken the test found only 61 passed the test. So our sample, the sample is this 90 teens, and out of this 90, only 61 passed the test. And the DMV, they claimed this number. Out of all those who take the test, 80% they pass. That's their claim. And we are trying to check if this is true or not, or if we agree based on our sample, do we agree with that claim? Okay, so the question is, does this finding or does our sample suggest that the passing rate for teenagers is as claimed by the DMV? Okay, so let's do this step by step. Step one is state your hypothesis. So my null hypothesis is P equals to P sub naught. Well, I don't have to use P sub naught, sorry. Okay. So this is just 0.8 because of the claim. So I'm trying to test the claim of the DMV, and that's 80%. So I have to convert that one to proportion. So I have to say P equals to 0.8. This is my null hypothesis. You remember the null hypothesis, it's a no change. We always use the equal sign. Now, how about the alternative hypothesis now? What do you think about the alternative hypothesis? P, we have this two, of course, but the in between, do I have to choose the not equal sign or greater or less than? What do you think, guys? Okay. No response? So here, there is no indication for me to pick the greater or less than. If you look at the last sentence, the question part, there is no indication. Okay, so I cannot choose the greater or less than sign. Therefore, here we use the no equal sign. Therefore, my alternative hypothesis is P not equals 0.8. And then the next step is my model, and I have to check the conditions. So here it says 90%, 90 randomly selected, which means the independence and the randomness is guaranteed because they pick the sample randomly. Therefore, we are okay with that one. Independence, randomness. Okay, and then what else we have? Okay, yeah, 10%. And again, you don't have to calculate this 10%. Just look at the problem. What is your population? Well, our population is all people or all those teenagers who take the DMV test, the driving test. And well, it's a large number. If we consider the whole United States, it's a large number, a large group. So 90 out of all this big group is obviously less than 10%. You don't have to calculate, just if you understand it well, then just you have to justify it, that's it. And the last condition is the success failure condition. Success failure condition. Okay. And this one is, remember from confidence interval, n times p, which in this case is n is 90, and p is our p sub naught, which is the claimed value, so 0.8. And this value is 72. This is obviously greater than 10. And then I have n times q, and this is 90 times, well, q is 1 minus p, and this is just 0.2. So here I have, and this is 18. Again, this is greater than 10. Therefore, the success failure condition is again satisfied. So all the conditions, all of them are okay. So we can go and do our test. Now, what is the model? If these are satisfied, then of course we mentioned here, the model is Z model, or the normal model. So my formula to find the standardized value is Z equals to P minus P hat minus 0.8. Well, I will just use the notation P sub naught over the standard deviation of P hat. Okay. Now the next condition, the next step is to find the values now. Okay. Here in step 2, I'm just trying to check the conditions and figure out what my model is, because we have 2 models here in this course that we learned. One is the Z, the one that we use the Z, which is the normal model. And the other one is the T distribution, which we use for mean, for finding confidence interval about mean and for testing a hypothesis about mean. Therefore, you have to pick one of them, either the Z or the T. Okay. So always remember, if it is about proportion, use Z. If it is about mean, use T. Okay. So step 3, the mechanics. Well, the mechanics here means just the calculations. All the calculations that we do it at this step. Now, what is our n? N is 90, and x is 61. This is the number of teens who passed the test. Therefore, p hat is x over n. So this is 61 over 90. And this is, let me use 61 divided by 90. And this is 0.68 approximately. Yeah. Okay. And then what is the standard deviation of p hat? And this is given by p sub naught q sub naught over n, and p sub naught is the claimed value, which is 0.8, and Q sub naught is 1 minus 0.8, which is 0.2, and N is 90. And then if we calculate this one, this number looks like 6. This is 0. Okay. And this is 0.8 times 0.2 divided by 90. I got 0.042. Okay, you can check this one. Okay. Now we have this, and the next is to find the z-value.
If we're finding the standard deviation of p hat, why do we use p naught and q naught?
Why do we use p naught? That's a good question. So,
and not p hat and q hat.
Not p hat. So I was trying to mention this somewhere in here. Yeah, somewhere in here. Okay. So what we do is, the main thing is the standard deviation. From the central limit theorem, the central limit theorem tells us that, you remember last time we used the simulation when we were, I don't know, during the normal time. No, it's not normal. So if we have, like, if we collect too many samples, and if we have, let's say, p hat 1, p hat 2, and so on, and if we put all these p hats from the same population, I mean, if we put them into histogram, remember, it would be a normal bell-shaped unimolar histogram.
Okay.
So that's why we are using the z-table. And of course, when it is normal, we need to know the standard deviation and the mean of these p hats. So the mean of p hats is p itself. Whatever the population proportion was, that will be mean of this new data. So our new data is p hat, these p hats. We're assuming, like, hypothetically, we are assuming we can collect too many samples. And the standard deviation of p hats is given by pq over n. P is the population proportion, q is the population, the 1 minus p. So this is from the central limit theorem, or this is what we had using the simulation, if you remember, using zeros and ones. I think we took this one in class. Yeah. Now the question is, how about if I don't know p? If we don't know p, we use an estimator. Remember, if, for example, if we don't know mu, I use y bar or x bar, it doesn't matter. If I don't know sigma, I use s to estimate the sigma, right? So all these are just estimators. These are estimators, but the important ones are these ones. Not important, but the population values, the actual values. And this is similar to that one. This is the actual value, the standard deviation, and the standard error SE is the estimator. So when I have the population value, I don't have to use the estimator. When I have mu, for example, I don't have to use y bar. The reason why I use y bar is because I don't have mu. When I have sigma, I don't have to use s. But if I don't have sigma, I use s. So when we don't have standard deviation, like what we did here, when we don't have standard deviation here, we use the standard error because I don't have the p here, okay? But since here we have the p sub naught, or the claimed value, I use the standard deviation here, okay? So the reason, in short, is because we have the population proportion. Okay. This is the population proportion, the claimed value. So since I have that one, we just use the standard deviation. You don't have to use the standard error. This is a very good question, and somehow it's probably you have encountered it, because it could be kind of confusing, because when you deal with confidence interval, you use the standard error, but when you do the hypothesis testing, you use the standard deviation. So you have to be careful on that. Did I answer your question?
Yeah, thank you.
Okay. All right, so now the next question is, what is our z-value? Okay. Okay, so z is given by, what is the p hat? Yeah, z is given by p hat, which is 0.68 minus the claimed value is 0.8 over the standard deviation is 0.042. 0.042. And if we calculate this one, I guess it is a negative number, and 0.68 minus 0.8 divided by 0.042. I got negative 2.86. Okay, now the question is, what does this mean? Okay, what does this z gives us, or this z value means to us now? So remember, this z is a normal model. So suppose we have this curve, because we know it's a normal, so I can just draw that one. And the center is always the mean. In this case, it's P. Okay. Now, remember, up to now, we're assuming the null hypothesis is true. Okay, that's our assumption up to now, because we haven't proven that one otherwise. So my P is the claimed value, which is 0.8. Okay, so the center is 0.8. Now, if you remember, what does this mean? We are talking about this p hat. This is the p hat, which we found it from our sample. This is what we have. This is our evidence, by the way. So when we standardize this value, we got this value. This is the standardized value of our p hat. And what does that mean? If we remember, we would use standard deviation as a ruler when we say that. This z value is a distance from the center. So since we have negative now, it's to the left side. Therefore, let's say if the value is somewhere in here, negative 2.86, or sorry, here we have p hat. And in terms of z, this is z equals to negative 2.86. Okay, so this negative 2.86 is this distance between p hat and p. Now, what can we say about this? Are they close to each other, or are they far from each other? Now, here is the important thing now. This part And on the other side, we have, again, the positive part of that critical value. And on this side as well, we have some area. Now, this is what we call the sum of those two areas, the p-value. Okay, this is what we call the p-value. Now, I'm going to go up to the definition and see what p-value says. So the p-value is the probability of seeing data like our sample. Okay, our sample is negative 2.86. So it's observing or seeing data, the probability of seeing data like our sample, or more unlikely data. So if it is more unlikely, what do we expect? We expect it to be further, to go further and further to the left, and similar to the right. Okay, so if it is more unlikely, the more unlikely it is, it's the more further it goes from the center. Therefore, the p-value is the probability of seeing data like our sample, or more extreme or more unlikely data, given the null hypothesis is true, given the claimed value is true. So if this were true, then this is the probability of observing data like our sample, or more unlikely data. Now, how small is this p-value? If it is large, let's say it starts from here, which means it's bigger. So when p-value is big, our sample data is closer to the mean, right? When p-value is smaller, which means if we go further, if we go to the left, the p-value or this area becomes smaller and smaller. So if this area is small, then it tells us that our sample is far from the center or this claimed value. Therefore, we would agree that this is not only, or it cannot only be by chance, this difference, which means we don't agree with this null hypothesis because our sample is too far from the center. Therefore, either this is not true, or there is something incredible happened, like when we select our sample. Okay, therefore that's when we say we don't agree with this one, when p-value is very small, which means when our sample is very far to the left or to the right, we say we don't agree with this one anymore. Okay, we don't have enough evidence to accept this one. But when our sample is close to this center or to the claimed value, we say, okay, we fail to reject it. We don't have enough evidence to reject this one. Okay, so that's the idea behind p-value. Therefore, going back to the p-value definition, or when p-value is very low, when this is low, then either H0 is not true or something remarkable occurred. So reject H0. Okay, when p-value is very low, we reject H0. When p-value is high, we do not reject H0, or we say we fail to reject H0. Again, remember, we don't say accept H0. We don't accept, we don't know if it is true. Do not say H0 is true. Okay, I'm not sure about that. Just, you don't have enough evidence to disprove it. Okay. Now, I hope we don't have any problem finding z value up to here. Okay, because we have been doing this one, and hopefully you remember that. And so here, up to this step, we have z value. We found z value, and the next step is, because we want to decide whether to reject or not reject H0. So I have to find p-value now. I have to find p-value. And this p-value is to the left of your calculated z-value. This is your calculated z-value. We got negative 2.86. So the area outside this one, to the left or to the right, will be the p-value. So here I would like to mention three things. I don't know. So one is when let me put it here. When H sub A, sorry, is P not equals to 0.8. If this was your alternative hypothesis, then your area would be on both sides. This is the difference that I was mentioning earlier. Okay, so the area would be on both sides because of this one. If your alternative hypothesis, we're only talking about alternative, I don't care about the null hypothesis now. If HA was P greater than 0.8, for example, if this was our alternative hypothesis, then suppose this is the calculated Z value. This is what you calculate. Okay, and only this side becomes now your p-value. Only one side. You forget the left side because of this one. So always it's to the direction of the inequality. So here it will be your p-value. Okay. Your p-value here. And if H sub A is P less than 0.8, then here you have the Z calculated value, and this will be your p-value. Okay, so depending on what your alternative hypothesis is, you pick either one side, only the left side, or the right side, or the sum of the two sides. Okay, all this depends on what your alternative hypothesis is, and that's why I was saying we have to be very careful on picking our alternative hypothesis. Now, coming back to our problem, of course, our alternative hypothesis is two-sided, which means it's a not equals hypothesis. Therefore, our p-value is on both sides. Now, if we remember, this normal curve is symmetric. Therefore, these two areas are the same. So finding one area is enough, and then you just multiply by 2. Okay. So here I have negative 2.86 and I have positive 2.86. So in this case, I have two critical values. One is the positive side and the other is on the negative side. And I am trying to find this shaded part. Okay, and this one as well. So to find this one, either you can use the Z table or you can find the okay. So either you can use the table or you can use the StatCrunch. I would recommend you to use technology for this one because it's for you. If you get used to that one, it's much more easier. Now we don't have in-class test, so you don't have to worry about that. So let's see how we can find using the StatCrunch first. So to find the z value, the p value, you just go to stats, calculators, and then here normal, because we are dealing with a normal model. And here, what do we know? So we are trying to find only one side. You don't have to worry about the right side now, because finding one side is good enough. Just multiply it by 2 then. You don't have to worry about finding the other side. So I wanted to find only the left side. And the z value that I have somewhere in here is negative 2.86. And that one, I will write it here. Negative 2.86. So, and this inequality, I use the less than sign, or you can find the right side, it doesn't matter. So we compute this and we get this area, 0.002, which is kind of small. So we have this area is 0.002. Now to find the p-value is given by 2 times 0.002. This is only one side, which means the left side. And of course, on the right side, I have the same value. So we just add them or multiply it by 2. It's just the same. So I have 0.004. So this is my p-value, which means the area, the sum of these two areas. Now, our next step is conclusion. So based on what we have, what do we say, or what do we conclude? Step number 4. And here, let's compare p-value and alpha. Now, what is our alpha? Let me write it here. What is the value of alpha? Now, if we go back to the problem, it doesn't say anything about confidence level or confidence of or significance level. Okay. Now, again, if nothing is mentioned about the confidence level, always use 95% confidence level. You remember that was the commonly used one, the most used one. So we use that one if it's not given. If it's given, of course, you use that value. But if not given, always use 95% confidence level. So if it's given 95%, if you wanted to use the 95%, it means the middle part is 95%. Because here we are talking about two-sided, okay? Therefore, the middle side, the middle area is 0.95, and the leftover is 0.05. Therefore, alpha is 1 minus 0.95, and this is 0.05. Okay, therefore my alpha is this value. Now we compare this alpha and my p-value. Already I have p-value here, I have alpha here. Which one is greater? Of course, the alpha is greater. And what do we say when alpha is greater? Now, since
Reject H.
Sorry?
Reject the null hypothesis.
We reject the null hypothesis. And why is that?
Because p-value is less than alpha.
Very good. P-value is less than alpha. So p-value let me write down here, is less than alpha. We reject the null hypothesis, which is H sub naught. Okay. Now, this is my conclusion, of course, but I have to interpret this one. This is, of course, if you are a statistician or if you know this course, of course, you know it. But you have to answer the question. The question is, do we agree with this one? Do we agree with the DMV claim? So you have to answer the question in the context of this problem, okay? Because we don't want to be more too technical. We don't have to use the technical words. You have to answer this one in the context of the problem. Now, what do we say? Do we agree with this, with the claim? Well, since we rejected it, we don't agree with that one. So we just write that one. So we don't, you can use your own English, it doesn't matter. I mean, this is just interpretation. So we don't agree, or we don't have enough evidence to agree with the DMV claim. Okay. So this doesn't mean the claim is not true, but based on what we have, based on the sample, we don't agree with it. But who knows, if I pick a different sample, probably I may agree with their claim. And that's why we say, we don't say it's not true. Okay, we're not sure about that. So we have to be careful when we interpret our conclusion. All right, do we have any question after this? Okay, so there is another question, another example here. I don't know if I have to, or maybe, yeah, let's do this one. And then maybe, by the way, let me ask you, do you want another meeting? Like, shall we arrange on Thursday? Because that's what we are doing with my another class. Since the exam is next week, if you want, we can arrange another meeting the same time on Thursday. Same. Yes. Okay. Yeah. So I will just
record that one too.
Sorry.
Can you record that one too?
Yes, I will. I will. Yeah.
Is there going to be, is this and what we went over last class, so like what's in our homework, going to be what our test is over, or is there more left for you to teach?
No, coming, we don't have any left. This is just from the past.
So it would just be like more, it would be working through more problems just to get more comfortable with it?
I don't know if we can finish this one today because we have another full topic here, like hypothesis testing for mean.
Oh, okay.
So I don't think we can finish this. So that's why I'm saying it would be a good idea to.
So that's what we'll learn next.
Yeah. Okay. Hypothesis testing about me. Okay.
Thanks.
So for now, let's just do this example and then we can do this hypothesis test for mean next time. Okay. Basically, I mean, it's more or less similar to that one. The only thing is we use a different model now here. So, I mean, if you understand it, if you watch the videos or something, then that's okay. If not, I will just have another meeting. Anyone who wants can join. All right. So let's look at this problem now. A multiple choice test question has 4 possible responses, and the question is designed to be very difficult with none of the 4 responses being obviously wrong, yet with only 1 correct answer. So the correct answer is just 1. And we have 4 possible responses. It first occurs on, okay, by 400. Okay, so we have 400 students. And the designers test whether more people answer the question correctly than would be expected just due to chance. Okay. So how can we set this problem now? How do we set the hypothesis test now? What can you say about this? Try to understand the question first. And then let's think about how we can set the hypothesis test. So H sub naught, what we have here is, because the possible response are 4, by chance, the probability of answering the question correctly, because there is only 1 correct answer. So by chance, we have 0.25 probability to answer it correctly. Okay, because there are 4 possibilities. Now, again, the most important one is this one. Now, what is my alternative hypothesis? Is it a null equal? Is it a 2-sided or 1-sided? What do you think? Anyone? Any idea?
One-sided.
And why is that?
Because you're testing whether more people answer the question correctly.
Exactly. So we want something like this, some indication like this one. Okay. So since we have this indicator, this terminology, which indicates that we need to use the right side hypothesis test or alternative hypothesis test, then we use the p-value, p greater than 0.25. Okay, so this is our alternative hypothesis now, just because of this indication. So that's why I was saying we have to be careful on this. Just look for some indication in the wording in the problem. Okay, and then we have the model of the model is just the z-value. I'm not going to repeat everything that we talked about. So here we have p hat minus p sub naught over standard deviation of p hat. And the conditions, we're going to assume they are satisfied just for the sake of doing this problem. And of course, if we are talking about very big number, then this 400 would not be that large. So let's just jump to step 3, the mechanics. Now, what is p hat? Here in part B, we have, of the 400 students, 125 correctly answered the question. Okay, so we have this, and we are asked to find the p-value. Of course, we have to find that one. So p hat is 125 over 400. and this value is 0.3125. Okay, and then let me put some more space here. And after that, what we need to find is the standard deviation. And the standard deviation, we don't use this value. You don't have to worry about that. We just use the claimed value. And that is 0.25 times Q is 1 minus 0.25, which is 0.75, and N is 400. And this value is I got 0.022. Okay, and then the next is to find the z value. And this is p hat, which is 0.3125 minus 0.25 over 0.022. And okay, so I got again 2.84, which is close to the first one. Okay, so next is we need to find the p-value. So all this is just step by step. We use this z value to find our p-value. So to find the p-value, let me draw the. Now, what do you think? What is the p? On which direction is the p-value now? Again, it depends on the alternative hypothesis, and alternative hypothesis is p greater than 0.25. So the p-value is always in the direction of this inequality. So since this inequality is a greater sign, then our p-value is on the right side of this value. So if this is 2.84, then the area to the right of 2.84 is what we call the p-value. Therefore, p-value, the p-value is, now remember here, we don't multiply it by 2 because we don't have on this side, on the left side. Do not multiply it when it's one-sided. So let's go to the table, to the StatCrunch or table, it doesn't matter. So here I will change this one to greater sign because I'm trying to find on the right side. And I will change this to 2.84. And the area is, again, more or less the same, 0.0023. Point 0.0023. So that's our p-value, and this is what we use to decide. So what is our decision now? Step number 4 is conclusion. And well, do we have anything about alpha? Yeah, here it's mentioned. We are told to use that one. But even if not, we use the same alpha, this 0.05. If it's not given, that by default we use that value. Okay. So since p-value is smaller than 0.05, which is our alpha, we reject H sub naught. Okay. And here we are saying if we reject H sub naught, we are agreeing with the alternative hypothesis. And the question was, we are trying to find if more people answer the question correctly than would be expected just due to chance. So due to chance, we would expect 0.25 times 400, which is just 100. Out of all this 400, we would expect only 100 to answer the question correctly. Okay, but here we have 125 who answered it correctly. So are these 25, for example, are they just by chance, or it's they answer it correctly? I mean, is it far from the 100? Can we say statistically significant? Well, yes, it's significant because of this one. So there are more people who answered the question correctly than we would expect by chance. So that would be our conclusion. And I guess that would be it for today.